Hi there, everybody. For those of you watching the recording, a couple of web work questions to start with here today. All right. So 3 and 10. All right, the skis problem. Cool. So did anyone figure this one out? Probably not many people have tried yet, huh? Any thoughts on how to do this one? Add all the number of customers times the probability for A. For a what, Lucas? For the expected number of customers. Okay. So maybe we should find that first, right? So the expected number of customers. So how would we figure that out? Okay, so David, that's right. Yep, you multiply the probability times the number of customers and add them up for each category, right? So, okay, so we're going to have 0.075 times 85 plus, let's do a few more here, 1586, 487, one of the last two here, 2.2 times 88, 175 times 89. All right, and that gives us 87.25 for the expected number of customers. Okay. And that's sort of the main thing that we're going to learn today from section 9.8 is about the expected value. And the basic idea of it is there's a bunch of different categories of things that can happen. And you, to get the expected value from what may happen, you take the outcome from each situation multiplied by its probability and add them all together, right? Which is what we did here. We just multiplied the probability times the number of customers and added all those up. And here's the expected number of customers, right? Okay. So what about the rest of these guys, B through F? What's going to happen here? So maybe we'll start with B, right? So what would the expected profit look like? Well, if Mike has 85 sets of skis available, okay, 85 times the price. Okay, so that's part of it. But just in English, if Mike has 85 sets of skis available, how many of them are going to get rented? And with what probability? How many customers? Yeah, 85 or less. Well, Nathan, let me explore what you mean by that. So how many customers is it possible that Mike could get? What are the options available? Yeah, all 85 will be rented because Mike is going to get either 85 or 86 or 87 or 88 or 89 customers. Those are the only options, right? Because if you look at the probabilities here and add them all up, that comes out to one right here, right on this top row. So these are the only possible amounts of customers that Mike could get in a day, right? And so if 85 sets of skis are available, and that's the smallest number, then Mike would be guaranteed to rent all 85 sets of skis. Some people won't get a pair. Mike's going to run out, right? If only 85 are available and 88 people come in, 3 people are not going to get skis and they're going to get turned away, right? So no matter what, if 85 sets are available, Mike's going to rent all of them every time. People good with that logic? Does that make sense? Any questions there? Okay, so in that case, right, we're going to, well, we're not going to multiply by this probability because we know with probability 1, right, 100% of the time, all 85 sets of skis are going to be rented, right? So how can we then compute the profit? Basically, so Nathan, where you made a mistake is we're not looking at exactly the probability that 85 people will come in. We're looking at the idea that 85 or more people will come in, right? And that's 100%, right? So we would do 85 times 8. Okay, so David, that's part of it. Yeah, right. 85 times 16 minus 8. Right. So, oh, okay. So David, I'm sorry, you had all of it, right? Because you did the 16 minus 8 in your head. So it's going to be the amount of profit or sort of the income. The profit is going to be the income minus the cost. I don't know if those are the right words. I'm not a business guy. Okay. But, there's money coming in, there's money going out for every pair of skis, right? So you subtract those, like Haruka said, you get 8, like David said, that's perfect. So 85 times 8 should be the expected profit, right? Do people have questions there? Does that make you happy? Makes sense. Okay, cool. So what about 86? What are we going to do here? So now in terms of customers, there's 2 things that could happen. Okay, there's a 7.5% chance that one of them doesn't get rented because there's a 7.5 or 0.075, however you want to look at it. But if for percentage, you move the decimal point over 2 spots, right? So there's a 7.5% chance that we have 85 customers. I guess that would make a 92.5% chance that there's 86 or more customers. So there's 2 different things that could happen. We could get 85 or we could get 86 or more, right? Now, in that case, with those 2 cases, we're going to add up the profit that we would expect from those 2 situations, right? So if 85 customers come in, we'll deal with the first situation first, right? What is the expected profit if 85 people come in? Okay, 85 times 8 minus 8, or 85 times 8. Okay, so maybe explain in English what you're doing there. What do you guys think about that? Okay, subtract off the cost of the pair that doesn't get rented, or I would say that may not get rented. So sort of what's happening here is that with 86 sets of skis, right, the cost of maintaining the skis each day is always going to be there. Whether they get rented or not, you still have to maintain those skis, right? So there's going to be sort of, if we talk about the loss first, right, the cost of maintaining them, that's always going to be 86 times 8, right? And that's going to be negative, right? But what's the income that Mike could receive? Well, there's two different things that could happen. He could rent 85 sets of skis, or he could rent 86 sets of skis, right? And those have different probabilities. So there's a 0.075 chance times 85 times 16. That's how much money Mike will make if he rents 85 sets of skis, or there's a 925 or 92.5% chance that he rents 86 sets of skis times 16 bucks per set, right? So you see what I did there? The loss is always going to be all 86 of them. Now there's a 7.5% chance that he rents only 85, 92.5% chance he rents 86 of them, and adding those up minus the total loss should give us the expected profit. What do you guys think about that? Does that part make sense? Questions? Okay, so let's see if we got that right so far. Yes, we did. Okay, so so for the rest of it, I think you should be able to sort of take that idea and move it forward. You know, how many sets of skis should Mike have ready to maximize the expected profit? Well, that's just the biggest answer you get from letters B through F, right? And if it's you know, 87.5 is the 87.25 is the expected number of customers, you would think that the expected profit would be at maximum, probably at 87 or maybe 88, right? Because this is a fractional amount, so we're not really sure which way it's going to swing, but probably 87 or 88 will be, you know, the highest expected profit, because if Mike tries to have 89 skis, sets of skis available, then that loss, you know, might compensate, might eat up more money than the possibility of renting that last set of skis, right? So probably 87 or 88 is going to be, you know, the most advantageous amount for Mike to have ready to rent. Yeah. Are people happy with that? Any questions there? Nice. Okay, great. And Nathan, I think that was your question, right? So perfect. Okay, one moment here. And 10-2. Perfect. All right. So let's check out number 10 here. Sorry, my dog just got home. Oh, and this is the elevator question. Okay. So let's actually hold off on this one till we get a little bit more experience with the expected value idea. This one's a little bit tricky. So I'd like to hold off on this one. Nathan, why don't you remind me on Wednesday, and let's look at this one at the end. Does that sound good? I think it'll be better. Yeah, I think it'd be better if we have a bit more machinery set up so that you can understand it better. Okay, cool. So in that case, didn't see the 4.9 or 1.4 section. Okay, so Nathan, that's dependent on which edition of the book you have. So there was the stuff got kind of reorganized into different parts with the new edition of the book. But that is all talking about the stuff for next week. So does it say that for our stuff for this week? Because this week should just be, well, here, let's see. It does. That's not great. Oops, I'm sorry. So let me look at this here. well, for those of you that have the new edition, this is the graph theory stuff, right? Which I thought we weren't going to do till next week. Yeah, so the lab is not up yet. So that I'm going to put up on Wednesday. Wait, no, wait, no, the lab should be up. Oh boy. Okay, so things are screwed up here. One moment. Check up on this here. Oh, it's just blacked out. I see. So here. I don't know why that's blacked out. Should be able to fix that, I think. Yeah, thanks for letting me know. Okay, I don't know why that's hidden. Let me fix that. Okay, so that's right. And lab 6, okay, yeah, that's all correct. So this should be the random walk. Yep, okay, so this should just be blocked back in. Let me fix that for the other class as well. Thanks for bringing that up, guys. Appreciate that. Yeah, you will have a lab and a proof this week. Okay, assignments. Okay, and then while we're doing this, okay, so let me, does someone have the new edition of the book handy? And is that section 1.4 and 4.9, are those the graph theory, the intro to graph theory sections? I believe they are, but I thought we weren't starting that till next week, but maybe my schedule is different than what I thought. Okay, so those are fixed. Okay, good. Well, tell you what, doesn't matter because we're not going to get through more than 9.8 today anyway. So let's blow through 9.8 today, and then I guess we'll get a jump on the graph theory stuff on Wednesday, and we'll figure that out at that point. I was going to talk a little bit about 9.6 today as well, but I think we'll have time for that. Yeah, so let's do both. Yeah, it's gonna be great. Okay. Yeah, and then on Wednesday we'll have to go over the midterm as well. All right, cool. So so let me pop back over to the video here. Any other questions for me? Yeah, 1.4. Yeah, and 4.9 is handshake, which is also graph theory. Cool. Okay. Good. So I guess we'll jump into some graph theory on Wednesday if we have time. Okay, so I did want to talk a little bit about section 9.6, just do a couple of examples since we missed it last week. Maybe spend a half hour there. Do a couple more questions from section 9.7 as well, and then we'll get into 9.8 in the next hour. So section 9.6 is all about combinations with repetition allowed, right? So the way that we're going to approach problems like this is actually sort of a sneaky trick where we convert a question of this form back into a regular combinations question. So let me give you an example, and I think that'll help, right? Let's see, what's a good example here? Okay, so a person giving a party wants to set out 15 soft drinks and shops at a store that sells 5 different kinds. Okay, so this guy wants to buy 15 sodas and 5 types are available. Available, I don't know. I hate spelling. Okay, so how many different selections can you make? Or in other words, how many different combinations can you buy, right? And here's the idea, right? We want to take this question, Where, of course, when you're buying sodas, you know, if there's Sprite and Dr. Pepper and Coke and whatever else, you could get like multiple cans of Coke or multiple cans of Dr. Pepper, which is different than the kinds of combination questions we were talking about last week, right? Because last week we were saying, okay, well, you know, when you do a combination, you only get to pick one of each thing. Like in a deck of cards, there's only one of each card, right? Or with a dice roll, there's only one of each kind of number that comes up on the die, right? But now we have these sodas and you can get multiple Cokes or multiple Dr. Peppers. So we're going to need a different approach, right? And the idea here is with crosses and bars, okay? So what we're thinking about here is we have 15 sodas with 5 types available. And the idea is we're going to set up some slots like we did before, right? And so to do that, we're going to have 15 slots for the sodas, okay? But we're also going to have slots to divide up the sodas that we buy into categories, okay? Now, for example, let's say we had Coke, Dr. Pepper, Sprite, orange, and root beer, okay? So those are the 5 kinds, for example, right? Now what we're going to need is a divider between these categories, and then all of the slots inside right, will be the sodas that we get in each one, okay? So there's going to be sort of 2 kinds of things that we're putting in here. There will be slots. I don't know if I added this up correctly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 14. Okay, and then we'll just do one more X in here, and then the rest will be blank. Right? So there's 15 X's, which represent our 15 sodas. And then there's the dividers, which represent the transition from one category of soda to the next. Okay? So really what we're thinking about here is this is like one example of an arrangement of different kinds of sodas where, you know, the guy gets 3 Cokes, 4 Dr. Peppers, 7 Sprites, and 1 orange, right? But really what's going on is that there's another slot for each of the dividers. So really what's happening here is we're going to have 15 plus 5 minus 1 slots. Why do we have the minus 1? Well, if we have 5 categories and we want to divide them up, we only need 4 dividers to do that, right? And that's, you know, that's going to be true no matter how many categories we have. If we had, you know, 9 categories available, we would need 8 dividers to sort of split them up. It's always 1 less, right? So really what I'm asking is, if I have 19 slots, okay, so there's 19 slots, how many ways can I arrange the dividers, right? I could put 1 here, 1 here, 1 here, and 1 here, which means all of the rest of these are sodas. So we're doing some dividers, some sodas, and so 19 choose 4 is exactly right. This particular combination would be 2 Cokes, 6 Dr. Peppers, 3 Sprites, 2 orange, and 2 root beers, right? And so since we're choosing 4 out of these 19 options, it would be 19 choose 4 different possible combinations, right? And that's thinking about where you would place the dividers. How else could you think about it? What else could you think about where to place rather than where to place the dividers? Good, where to place the sodas. And so what would that be equal to? What choose, yeah, good. 19 choose 15. Which had better be equal, right? And in fact, they are equal. 19 choose 15 is equal to 19 choose 4. Why is that? Like, how would you know that? Yeah, the binomial theorem, right? These correspond to numbers inside of Pascal's triangle. And remember, Pascal's triangle has this symmetry to it, right? Where we've got 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, right? There's this symmetry line right down the middle, right? And if you go all the way down to the, 19th line, where you have 1, 19, yada, 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 all the way up to 19 and 1 on the other side. Well, if you count in 4 from the left, that'd be 19 choose 4. Count in 4 from the right will be 19 choose 15 coming this way. And those two numbers will be equal because there's this sort of horizontal symmetry that Pascal's triangle has, right? So you would know that these guys are going to be the same. What do you think about that? Does that make sense to people? Yep. Cool. Questions so far? Okay. So in general, for combinations with repetition, the number of choices available from n objects of R type. I think that's right, isn't it? Yep. Nope. R objects, R combinations with repetition allowed. That would be, okay, n objects of R types is what? Can you see the formula for R and N here? Okay, so David, you're pretty close there. We've got N plus R minus 1, choose R minus 1, or choose N, either way, right? Because here we've got the N objects, which is 15, right? Or we could do choose R minus 1. Either way. Right? Because this would be, the 5 minus 1 is 4 types. That's this one, right? Or we could choose 15. Either way, they're equal to each other. What do you guys think? Okay, so let's try another question here, right? So here's the next part of our soda question. So let's try one that's a little bit more complicated, right? 15 sodas, 5 types, at least 6 root beers. Okay, so this guy he has lots of guests that like root beer, so he has to get at least 6 root beers, right? So Now what's going to happen? So let's lay out our slots again. So we got 19 slots. Okay, there's our 19 slots. Let's say that root beer comes first, just to sort of keep that easy, right? So if we have at least 6 root beers, right, how does that affect our placement of crosses and bars? Yeah, right. There's an immovable block of 6, or I guess I said root beers last, so we can put them last, right? So we know that there's, we'll put RO for root beer, or maybe RB for root beer, huh? RB, root beer, root beer, root beer. Okay, we know there's at least 6 of them, right? So that's our immovable block of 6 root beers, but there's at least 6 of them. So there might be more. He might be, get more root beers. So what now are we placing exactly? What choose what is going to be sort of our response here. Yeah, 19 minus 6, choose 4. So there's, there's these 13 slots remaining, right? So we would have 13 slots, and we're going to choose 4 barriers, right? So maybe I could put them 1, 2, 3, and 4, which is going to mean I get 2 Cokes, 1 Dr. Pepper, 2 Sprites, 2 orange sodas, and in this case would be 8 root beers, right? That would be one option. But out of these 13 slots, we're placing 4 dividers, which is going to divide up our sections into the different kinds of soda. What do you guys think? It's good? Okay, so let's do one more. 15 sodas, 5 types, at most 5 root beers. Maybe the store is almost out of root beer, right? And so the most that you can buy is 5 of them. That's all that's left on the shelf, right? So now what are we going to do? We could add separate cases. Yep. So that would work, but that would be the long way of doing it, right? Because you could get 0 root beers or 1 or 2 or 3 or 4 or 5. So it'd be adding up 6 things, which would take a minute to compute. But there's another way of doing it. Anyone see the sneaky way here? Yeah, well, close, Lucas. Not 1 minus that, but what minus at least 6 root beers. So you've got the second part right, but what are we subtracting off of? Good. The total number of choices, the one that we got up here, right? If there's no restrictions, right, then that's all the different choices you could get. Okay. The situation where you get at least 6 root beers and at most 5 root beers, those form a partition. Those are disjoint in terms of the number of choices you can get inside the total number of options, right? And because they're disjoint, there's no overlap. We could take the total, subtract off at least 6 root beers, and we'll get, as a result, at most 5 root beers. So what we would get is 19 choose 4 minus 13 choose 4. Right? Or you could do it David's way. It would just take a little bit longer. You could say, okay, what's the situation with 0, 1, 2, 3, 4, or 5 root beers, and add all of those up. Either way works. This way is just a little shorter. What do you guys think? It's good? Okay. So let's try a different kind of question. Do this actually. Okay. So we're wondering about x1 plus x2 plus x3 plus x4 equals 10, where for all I, x sub I is greater than or equal to 0. And we're wondering how many different arrangements can you have for x1 through x4, right? How many choices for the x sub I? So how could I use the same idea to solve this question, do you think? The numbers as types. Okay, so that's, I think you're right, David. Can you say more about that? Okay, so 1 through 9 would be, oh, okay. Not exactly, right? So you're close. Let me ask you a question. What would the dividers be? Right? So we had these dividers before, right? In this situation, what's the meaning of the dividers? Their sum equals 10. Can you say more, David? I'm still not quite sure what you mean by that. How many dividers would there be? Let me ask you that. Anyone else want to jump in? Yeah, 3. Yep, perfect. Good. So the dividers are going to be dividing up where the 10 units fall into each of these 4 variables. Because when we add up all the variables, we want to get 10. So basically what we're doing is we're distributing these 10 units amongst these 4 variables. Okay, so there are 4 types and 10 things that we're distributing. The things we're distributing are sort of like the sodas, but now instead of 5 types, we have 4, types, which means just which variable are we going to put the 10 units into. So we're going to have 13 slots like this. And we're going to have 3 dividers. Maybe we'll put it here, here, and here. Right? Now, if I do that, this is the section for x1, which is going to be 3 of them, right? Here's a section for x2, which is going to be, I guess, 4 of them. Here's a section for x3, which is going to be none of them. And here's a section for x4, which will be 3 of them, right? And this is one arrangement of x1, x2, x3, and x4, where we have 3 plus 4 plus 0 plus 3 equals 10, right? So how many choices do we have for the x sub I? What choose what? Close, very close, Amber. Not 12 choose 10, but remember we have 10 units and 3 dividers. Yep, so 13 choose 10. Very good. You're really close. 13 choose 10. That's if you choose where the 10 units are going, or you could choose where the dividers go, which is the same thing. 13 choose 3, right? Again, that's because of the horizontal symmetry of Pascal's triangle. These two things are going to be equal to each other. Yeah? Questions? Okay, so then let's try another one, right? Well, let's move on, right? So so what I'd like to do next is maybe I don't know, let's do at least one more question from section 9.7. So in section 9.7, does anyone have any other questions about 9.6 before we move on? People sort of get the idea there. Yep. Okay. So let's try this. So last time with section 9.7, we showed that A plus B, or I think we're using X and Y in lecture, but they use A and B in the book, so I'll just stick with the book's notation today. For binomial expansion, bless me. So for binomial expansion, we've got A plus B to the n is the sum from k equals 0 to n of n choose k times a to the n minus k times b to the k. And this is the binomial theorem. Okay. So how about this? Let's maybe go through this just real quickly and talk about why this is true one more time. Just a little review, right? Can someone explain to me what's going on with this equation? Why? Let's start with an example. Can someone give me an example of this equation? Like when would you use this thing? X plus y squared. Yeah, that's a great example. Good, good. So, or I'll do a plus b squared since we're doing a's and b's here, right? So if I have a plus b squared, what's that going to equal? Well, we're going to have a summation from k equals 0 up to n, where n is 2. So we're going to have a sum from k equals 0 to 2 of what? N is equal to 2 here, so we'll have 2 choose k times a to the 2 minus k b to the k. And if we go through that, what are we going to have? Well, the first term, k equals 0, we'll have 2 choose 0 times a to the 2 minus 0, which of course is just a squared, b to the 0, which is just 1. Okay? Plus, because we're adding, 2 choose 1, a to the 2 minus 1, b to the 1, plus 2 choose 2, a to the 2 minus 2, b squared. If we simplify this, well, 2 choose 0, there's one way of doing it, so that goes away. The b0 goes away, so we have an a squared. Here, 2 choose 1 is 2. There are two ways to do it. A to the first, b to the first. Here, 2 choose 2 goes away. A to the 0 goes away, plus b squared. What do you guys think? Look good? Okay, so let's do something a little bit interesting. Let's say that I want to find the sum of all the different ways of choosing some number of objects out of n of them. In other words, I want to find, well, let me do it this way. N choose 0 plus n choose 1 plus n choose 2 plus yada, 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 plus n choose n minus 1 plus n choose n. Right? Okay, and I want to know what this is. In other words, I want to add up all the different ways of choosing from n objects. If I choose 0 or 1 or 2, right? Yeah, this would have helped a bit in calculus to find those coefficients, right? Okay, so can you guys help me write this as a summation? Let's start with that, right? So where am I going to start here? What goes under the sigma? K equals 0, okay. And what are we adding up to? N, good. And what goes inside of our summation here? N choose K, very good. Okay, and I want to know what this equals, right? So this is just the shorthand way of writing it, so that was great. And I want to find what this guy's equal to, right? Oh, and you do have to be careful not to put a division sign in here. right? Because that is different than the choose notation, right? So you got to be real careful not to put a little slash inside of here because that'll change the meaning. Yeah, the NCK, the way that you typed it before is sort of, that's sort of the nice way of doing it, right? Yeah, cool. Okay, so here's the question. Can you see a way to use the binomial theorem to find what this thing is equal to? What part of the binomial theorem does this thing look like? Yeah, the right-hand side. It's like this, but without the A and the B, right? The A and the B have just kind of vanished, right? And all we have left is the sum of n choose k, right? Well, okay. So in that case, if A and B vanish, what do they have to be equal to for them to just sort of go away? Yeah, they have to equal 1 because we're multiplying by A and B here. So if we have 1 to any exponent, it's still going to equal 1. B is equal to 1 to any exponent, that still equals 1. So actually, let me do this. Uh, nope. There we go. Close enough. Sum from k equals 0 to n of n choose k times 1 times 1, right? So A equals B equals 1, right? In that case, if A and B equal 1, then you can look over to the other side of the equation, which means we must have 1 plus 1 quantity to the n if A and B both equal 1, and so our grand total is 2 to the n, right? What is this saying about Pascal's triangle? Yeah, each row adds up to 2 to the n, which we can check, right? So if we have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Well, let's look at all the row sums. And we've got 1, 2, 1, 2, 1 is 4, 1, 6, and 1 is 8. That makes 10, 14, 16. So it appears to work. Right? Looks like we have a power of 2 for each increasing row. Is everybody happy with that? Okay, cool. So let me check your midterm real quick and make sure that I'm not doing a question from it. I think the next one is on your midterm, but let me double check here. I don't even have it. Okay, one moment, please. Okay, yeah, that one is on your midterm. Okay, in that case, yeah, then I think we're just good on that. Yeah, I think we're good. Okay, so okay, so we have another chat comment here. Sean says, you can build each next row in the triangle by adding the terms for the previous row so that each term is added twice. Yep, that's exactly right. So the way that you get that 6 in Pascal's triangle is it's 3 plus 3. So you add the two terms, above the number to get the next one. 3 plus 1 gives you 4, right? So if you want to do the one underneath here, it would be 4 plus 6 gives you a 10. So the next row would be, you always start with a 1. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is another 10. 4 plus 1 is 5. Next one is 1. And of course, if we were to add these guys up, it'd be 20, 32, right?
I
32.
guess what I was saying is that since you can build each row that way,
Mhm.
the 1 goes into the 1 to the 5, the 4 goes into the 5 into the 10. So like each term is getting doubled in the sum of all the terms.
Good. Yeah.
So
So
it
yeah,
makes
when
sense that
you
it's
add
that
it in,
powers of 2.
that's
Yeah.
right. This one is going into this one, and it's going into that one. So each number is going into two numbers below it, which means you double each number, which means it's 2 to the n, where n increases as you go down. Yep, that's a great way of looking at it. Yeah, definitely. Cool. Okay, so we're an hour in. Let's take a 5-minute break. And I'll let you guys think if you have any questions about all this stuff. And then we'll jump into section 9.8 when we come back. All right, see you soon. All right. Oh, and sorry, I should mention to those of you watching the recording, I did get a bunch of grades in. So you should definitely check your grades, see how you're doing. As far as business stuff is concerned, also we have the midterm due tomorrow night. So make sure to get that finished up. And now we're going to jump into section 9.8, which is the main thrust of it is about expected value. There's some other stuff in the beginning of the section about figuring out the probabilities of unions, but we've sort of already covered that in the previous sections. So I'm going to skip over that, and we're going to jump right to expected value. Okay. So if we suppose the outcomes of a process are real numbers, then the expected value which we can abbreviate EV, right, of the process is the sum of each outcome times its probability. In other words, the sum, I guess I should say, well, I'll say equals EV. The sum from I equals 0 to n, where there are n possible outcomes, of each outcome, A sub I, times the probability of that outcome happening is equal to the expected value. Okay. And I think this is made most clear with a few examples. So we're going to do a couple of examples here, right? So let's say that there's a lottery, okay? So we're going to play the lottery. And gambling really is sort of the most obvious way to talk about examples here, okay? Now, in our lottery, there's a lot of different things that could happen, okay? So in our lottery, it costs $5 to play. And 500,000 people are going to play. Okay. Here are the prizes for the lottery. Okay. We've got one grand prize at $1 million. Okay. We've got 10 first place prizes at $1,000. We've got 1,000 second place prizes at $500. And 10,000 third place prizes at $10. Okay, so here's all the information for our lottery. Costs $5, 500,000 people are going to play, and you can get any of these prizes, and here's the amount of each prize and how much that prize is worth, right? So what I'm going to do is calculate the expected value. Right? That's what I'm wondering. What's the expected value? So how should I approach this, do you think? Let me ask you this. What are the different outcomes that might happen? Because remember, for expected value, it's the sum of each outcome times its probability, right? So what are the outcomes here? The prizes. Yeah, good. Grand prize is one of the outcomes, right? You might win the grand prize. That's a possible outcome. Or you could win first, second, or third place. What's another outcome? You lose, right? You win nothing, right? Okay. So there's another sort of sneaky part to this, but let's do the prizes and then we'll talk about the sneaky part. Okay. So we can think about the expected value for each one of these prizes. Okay. So what's the expected value of the grand prize in this lottery? Just the grand prize by itself. Sure. So you got the sneaky part there, Natasha. There is one more thing that you know about the lottery is that no matter what, if you play, you're going to lose $5, right? So what there's a couple ways we could do this. We could evaluate each prize minus the $5 it takes to play, or we could add up the expected value of all the prizes and then subtract the $5 it costs to play at the very end. And I think that second way will be a little bit faster and easier way of doing it. So Natasha, while you're totally right, you can approach it that way. Let's wait till we subtract off the cost to play till the very end, right? So without that cost, right, for the grand prize, what would the expected value be? Okay, $1 million, that's part of it, right? Because remember, the expected value is the outcome amount, which in this case, the outcome would be $1 million, right? But then, yeah, times the probability of that happening, right? So this would be times 1 over 500,000, right? Which is going to equal how much? $2, right? So the expected value to play this game from the grand prize is $2, right? Because it's $1 million, but there's, only a 1 in 500,000 chance you're going to win it. And if you think about the words expected value, like how much do you expect this to be worth to you? Like what's how much value do you expect to get out of this prize? It kind of makes sense, right? Well, there's $1 million, but there's a very small chance of getting it. So how much is it actually worth to you? It's actually worth $2, right? Does that sort of idea make sense to people? I'm not sure I explained it the best possible way. Another way of thinking about this, the expectation is that if you were to play all 500,000 tickets, right, all 500,000 sort of chances to play this lottery, right, then you'd be assured to win the $1,000,000, right? So with, if instead of doing one out of 500,000, you played all 500,000, then of course you would get the million because one of those tickets would be the winning ticket, right? So then you would have, instead of 1 over 500,000, you'd have 500,000 over 500,000, which equals 1. And a million times 1 is, yeah, you get that whole million, right? Guaranteed if you bought every ticket, right? Yeah, that's right, Amber. It becomes closer to the real value as the repetitions increase. That's exactly right. Yeah, good. Okay, so what about this next prize? So there's 10 first place prizes at $1,000. So what would I do there? Mm, sure. So Sean, so since I already have that 1,000 here, right? So taking that into account for your 10,000, it would actually be times 10 over. Oh, and you, Sean, you wouldn't want to subtract one off. You still have 500,000 here. The same ticket could win two. Well, that's a great question. Let's see. How do they describe it here? Hmm. Yeah, so I think the way that they're describing it, you could win. Yeah, I think you could win two different prizes, right? So maybe maybe there's a big bucket of tickets, right? And they pull out a ticket and then throw it back and mix them back up and pull out another one, right? Yeah, so I think you can win multiple prizes in this game, which I guess is different than the way most lotteries work. Would it still work the same way if you could only win one prize? Hmm.
If
Yeah,
you
I
could
think
only win one prize, it would um lower the expected value of a ticket by some in tiny amount,
yeah, by a
right?
tiny amount. Yeah, so I think you're right, Sean, in saying that you would decrease the probability because it's still worth the same amount of money. You're just less likely to get it, right? So I think you're right to say that that probability would decrease if you're only allowed to win one prize. But let's say that you can win multiple prizes. It'll keep our calculation a little bit more straightforward, right? So how much would this first place prize be worth then? 1,000 times 10 over 500,000. 2 cents. Okay, great. Okay, how about this next one? So it's $500, and what's the probability of winning? Okay, 1,000 over 500,000. Okay, so how much is that one going to be worth? More than a cent. Remember, because we're timesing 1,000 in here, right? It's $1. Yep, very good. Right? And if you think about this, right, that grand prize is worth a lot of expected value because it's $1,000,000. That's a huge prize, right? Now this one, $1,000 is a lot of money, but there's only 10 of them. So it isn't worth that much in terms of the expected value because there's so few prizes available at $1,000. Now, $500, that's only half as much money, but there's 100 times as many of them available, right? If you think about that, right? There's half as much money, but 100 times as many. That means the expected value is 50 times as much. 50 times 2 cents is $1, right? So you can see this prize, this second place prize, is actually worth a lot more in terms of expected value than the first place prize. Lotteries are sneaky. They try to trick you, right, into thinking you have a better, that the expected value is higher for playing than it really is, right? That's how they try to trick people into playing the lottery. One of the ways, right? Okay, so what about this last one, the third place prize? $10 times how much? $10,000 over 500,000. Very good. Okay, which is going to be equal to 20 cents. So our grand total of how much we could win here is we're going to add all these up. Right? Which is going to be $3.22. And that's our positive expected value from playing this lottery, right? That's what we could win. But what are we going to lose? Now we're going to circle back to Natasha's idea. Yeah, minus $5, right? And what's the probability that you have to pay $5? 100%, unless you steal some of the tickets or something, right? But barring that goofy idea, right? Everyone has to pay to play, right? So it'd be minus $5 to play. And so the expected value of playing this lottery, as you said, sad face, right? Amber, is negative $1.78 is the grand total for expected value, right? So for each ticket that you play, you're losing $1.78, right? On average, right? Of course, if you buy 10 tickets and you win one of the first place prizes and nothing else for the sake of argument, then you're going to make a bunch of money, right? Because you spent $50 and you made $1,000, so you made $950. That's possible. It's just not expected, right? What's expected is that for each ticket on average, right, you're going to lose $1.78. People sort of see what's happening there? Any questions? Okay, so let's try another one. Let's say you're drawing balls. Okay, so here's what's going on. We've got yeah, since the $1.78 funds the schools, we all win, or maybe it funds uh, forest preservation or whatever the lottery pays for, right? So let's play a different game, right? Let's say that we're drawing balls, okay, and each of the balls has a number on it, okay? So the balls are numbered. Um, 1, 2, 3, 4, and 10. Okay. And let's say again it costs $5 to play. Okay. So there's there's a little bowl, okay, with some numbered balls in it, and someone mixes the balls around and picks one out, and that's how much money you get, right? And it costs $5 to play. Okay? And we'll say there's one of each kind of ball. Well, maybe I should make this more interesting. Let's say there's uh, one, one, three, 5, and 10. Make the game a little bit more interesting. Okay. Let's make all 3 of these ones. Change my mind here. Okay, that's better. So you have 3 $1 balls. So you make back a little bit, or you make back, the cost to play, or maybe you double your money, right? So we got 3 balls with a 1 on it, 1 ball with a $5, and 1 $10 ball, right? So what's my expected value going to look like? Well, what are my different outcomes? Okay, so my different outcomes are I could get $1, or I could get $5, or I could get $10. Okay, and then we want to multiply by the probability of each of those happening. So what's the probability that I get $1? Okay, 3 out of 5. $5, what's my probability there? Okay, 1 out of 5, which the expected value then if I multiply is going to be, that's going to be worth $1. And $10, the probability there is again 1 out of 5. So that's going to be worth $2. So the total expected value is $3.60 minus the $5 to play. So for the entire game, the expected value is negative $1.40. Now, Sean, I liked your way of doing it because it's a lot shorter, right? You can add up all the probabilities. I'm sorry, add up all of the worth, the outcome value for each ball, and then just divide by the total number of balls, and that's going to get you that same answer, right? Because if we have 1 plus 1 plus 1 plus 5 plus 10 divided by 5, well, that's going to be 18 over 5, which of course, again, is $3.60. Right. And if you just think about what it is to multiply and add these, this is the same thing, but just changing around where the parentheses are, right? Does everybody see that? Questions? Makes sense. Okay. So let's try one more game. Drawing face cards. This is always a fun game. You can play this one with your friends if you want to take their money, which is always fun, right? So you have a deck of cards, okay? And it's $1 to play. And you get $2 if you draw a face card. Right? So this is another negative expected value, you always, for any game, you want to be the house. You want to be the person running it, right? Well, not for any game. For most games, right? You want to be the casino, right? Because the casino is the ones that make all the money, and the reason why is to play their game is a negative expected value to the player, which of course means it's the exact same amount positive expected value to the person conducting the game, right? So if it's the state of Oregon, running this lottery, they're making $1.78 for every ticket that someone buys, right? If it's a casino doing this drawing the balls game, they're making $1.40 for every game that gets played, right? And if you play this game of drawing face cards with your friends, then you're going to make some money off of them, right? Which is, rude, but funny. So, take your pick, right? So it costs $1 to play. You get $2 if you draw a face card. Maybe your friend gets $2 if they draw a face card. Um, we'll say with replacement. We'll say we reshuffle the deck each time. Yeah. So it would be a lot more complicated without replacement. Definitely, Sean. Um, Yeah. So part of going to the casino is knowing what the expected value is for each game and playing games that have the highest expected value, which I believe is blackjack, right? Um, yeah, you definitely don't want to be playing roulette or craps. Those have not very good expected value, right? So, okay. So what's the expected value here? So it costs $1, but you get $2 if you draw a face card. Yeah, so perfect blackjack plays about 49%. So your 50% would be you break even, right? So you're almost breaking even if you play blackjack perfectly, right? Of course, then you can't be drinking all those free drinks there either, because then you're not going to play perfectly anymore, which of course is what they're banking on, right? Because for each game that you play, it's going to be, depending on the minimum bet, right? It's going to be probably at least $1. And then, each of those free drinks cost them $1, right? So they give you a free drink and then you don't play perfectly, and that they make back their money in, 2 games worth, right? Inside of 5 minutes, they've made their money back for that free drink, right? So there you go. But let's talk about drawing face cards, right? So what's my expected value going to look like? So it costs $1. What's the probability of that happening? So the expected value is minus $1 to the player times what probability? Okay, so David, you did the probability for the face card. Okay, so that would be plus $2 times 52, 12 out of 52. Because there's, well, I want to count aces as face cards though. So it'd be Jack, Queen, King, Ace. So there's 4 kinds of face cards. So I would say that would be 16 out of 52, right? I don't know. Are aces counted as face cards? I always thought they were. Right, they are. Okay. So what's the probability that you have to pay $1 to play? 1, right? 100%. So I have 2 times 16 over 52 minus 1. So I guess that's 30, 32 over 52 minus 1, right? So what's that expected value going to be? Yeah, negative 18 over 52. Here, let me Google that real quick. Negative 34 cents. Oh, sorry, negative 20 out of 50. Yeah, you're right. Negative 20 out of 52. Negative 38 cents. Yep. So if you play this game against your friends, on average, each game that you play, your friend is giving you almost 40 cents, right? And the reason why is because there's far less than half of the cards in the deck are face cards, but the benefit to you is only doubling your money, right? What if you were to triple their money? What would the expected value be then? Would it still be a benefit to you as the conductor of the game, or would it start to be a benefit to them? Yeah, it would be, right? So what if we change this around? So, you pay them 3-1 if they get a face card, which that starts to sound like pretty good odds, right? If someone walked up to you and said, hey, if you could draw a face card, I'll pay you back 3-1. That's not a terrible game. And the reason why is because the expected value is nearly zero, right? It's almost a sort of an even game, or I would call what's called a fair game. In a fair game, you'll make $0 and you'll lose $0 for every game that you play. Now this game's not very fair. You're paying almost 40 cents to play each game. But if we did 1 and 3, well, let's go back through, right? We have 1 and 3. Then we would have still 1 times 1, but instead of 2 times 16 over 52, it'd be 3 times 16 over 52, which is 48 over 52 minus 1, which you'll see is almost equal to 0, right? In this case, it only costs how much to play? 48 out of 52. Or maybe I should say 4 out of 52. This time it only costs about 8 cents to play. So if you wanted to be really sneaky and trick your friends, yeah, the 16, yeah, this is a 16, not an 18, because there's 16 face cards, 4 jacks, 4 queens, 4 aces, 4 kings, right? So there's 16 total face cards, 3 times that's 48. And so if you were really trying to trick your friends that are bad at math, I think this would be a good way to do it, right? You're still making on average, 8 cents per game. But to your friends who aren't good at math, it seems like a pretty fair game. And that's really how the casinos trick you, is it seems like a fair game. They're only going to make, 5 or 10 cents on each game that you play, right? But if you sit there for a couple hours and play, 100 games, they made $20, which more than covers the free drinks, right? What do you guys think? Does that all make sense? People happy with this? Okay, so let me ask you this. What if you played through the whole deck, right? Let's say that you played without replacement, right? And you played through the whole deck of 52 cards, doing the drawing face cards game. Then what would the expected value be to you at tricking your poor friend that's bad at math? $4. Okay, so how did you get that, David? You're close. Not quite. Yep, that's not quite the way to think about it. Oh, maybe it is. No, that does make sense, right? Because you pay $52, and you make back, yeah, so it should, I'm sorry, no, you're right, it should be $4, right? You lose $4 for each deck of cards that you play. The way that I was thinking about it was if you lose approximately 8 cents for each card. Oh, you know why I screwed it up? It's the approximately. I rounded. If I was to go back into here on Google, 1 second. Okay. So this is how much you're losing for each game. If I was to take that and multiply it by 52, of course, then the 52s would just cancel, and you're left with that $4 that you've lost. Yeah, so you guys had it right. I'm sorry, I got confused by the approximation there. Great. So if you play through the whole deck, you would make $4 as the one conducting the game. Cool. Okay, but you might lose some friends, so maybe don't do that. Right? All right. Any other questions so far before we jump into our next little exploration here? Okay, cool. So let's talk about our next subject, which is the gambler's ruin. Okay. Here's the game. It's a coin toss game. Heads means you win $1. Tails means you lose $1. What's the expected value for playing one game? 0, right? Because you're just as likely to win, assuming you have a fair coin, you're just as likely to win or lose, 50-50, right? So 50% times 1 is you win 50 cents. 50% times -1, you lose 50 cents. And so the expected value is 0. This is what's called a fair game. Is everybody happy with that? Does that make sense? Okay, so in that case, this is still problematic for the gambler. In fact, the gambler can still be ruined, even with a perfectly fair game. Okay, so here's what I mean by ruined is you spend all your money. You are now broke. Your money's gone, right? That's what ruined means in this particular context, right? So what we're going to say is that you walk into the game with a certain amount of money, right? So you start with N dollars. Okay. But you're a smart gambler in this case. So you start with N dollars, and you're either going to play up until you get M dollars or go broke, which means you have $0 left. Okay, so it's a nice idea when you're gambling to have some limits on what you're going to do, because you don't want to be ruined. That's always a bummer, right? So a nice thing to do is to start out with a certain amount of money, and you'll play either for, maybe for a set amount of time or a set amount of games, or until you reach a set amount of dollars, or more likely, right, if you go to a casino, you lose all your money, right? So in this case, what's the expected value of the game, right? So now there's this whole other structure of strategy on top of it, right? Now it's still a fair game, right? If you play one game, the expected value is 0. But we're not talking about playing one game. We're talking about you walk in with N dollars and you play either until you reach your goal or go broke, right? So what do you guys think? How should we approach this? Any ideas? Yeah, we would assume m is greater than n, but it doesn't have to be, right? No, I guess it does have to be, because otherwise we would never go broke. If m is like less than n, then we would, then we would stop before going broke. So yeah, so we'll assume m is greater than n. Yeah, that's a good assumption. Thanks, Sean. If m's greater than n, it's more likely you'll get to negative n than get to m. Well, that depends on what m is, I think, right? Which we're going to see when we solve this little equation here, right? So really what I'd like to do here is I want to know the probability of winning, and in this case winning means getting to m dollars and quitting, right? As soon as you get to m dollars, then you stop, then you won. Let's say maybe you're trying to double your money, right? So if you're trying to double your money, let's say you start with $100, right? Then you would either play till you get to $200 or back down to $0, right? So that's just one example of n and m. But really what I'm looking for is I'd like a formula where I can plug in how much I'm starting with, how much I'm trying to get to, and then see the probability of win or loss, right? Where win is that I get to my goal, loss is that I go broke and I'm ruined, right? So I'm trying to find a probability for each one of these two outcomes, right? From there, I could find the expected value, right? Because it'd be the probability of this happening times m dollars plus the probability of this happening times $0. So that would just be plus 0, right? So the expected value of my game would be, the probability of winning times the amount that I would win, right? It's a little bit like the interest formula in the sense that you can express it recursively. So it is similar in that regard. How could we recursively express what's happening in this game? Any thoughts? Okay, so let me help a little bit. Let P of K be the probability of having K dollars. Okay, so P sub K. So, P sub 50 would be the probability that you have $50, right? You need M. Okay, so Sean's saying you have M minus N heads in a row, which changes on each toss depending on whether you win or lose. Well, they don't have to be in a row. You just have to have more heads than tails overall. But they don't necessarily have to be in a row. You just have to get, they don't have to be strictly one after another, but you do have to get those heads before you get those tails. Otherwise, you would go broke too quickly, right? So it doesn't have to necessarily be strictly heads, 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 heads like that. But you are going to have to maintain, more heads than the number of tails if you're going to be making money, right? Right. Okay. Cool. Cool. So let me ask you this. You have the probability of having K dollars, right? And we can come up with a formula for this. And I want it to be a recursive formula. So how could you end up with having K dollars in terms of what happened in the last round, right? So each round is you bet $1 and you either win or lose, right? Well, you toss the coin and you either win $1 or lose $1, right? So if you have K dollars at some particular round, what happened on the last round? Two possibilities. Either won or lost. Okay, so let's represent each one of those, right? So if you won, how much money did you have? And what was the probability of you having that win? Remember the OR rule, we have addition here. Yeah, K minus 1. So you either had K minus $1, right? P sub K minus 1, K minus $1, right? And you won, what's the probability of that happening? Yeah, 1/2, right? Or there's a 1/2 probability that you lost from having K plus $1. Yeah? How about we multiply this whole thing by 2, both sides of the equation? Then we have 2 P sub K equals P sub K minus 1 plus P sub K plus 1. Now what can I do? Anyone remember how to solve one of these from last term? Or maybe let's rearrange it and then solve it. Does anyone know what kind of equation this is that we're trying to solve? Yeah, we want to find the characteristic equation. So this is a linear homogeneous recurrence relation, right? The kind that we were looking at in section 5.7 and 5.8 last term. Right? So I could rearrange this to say, well, P sub K plus 1 equals 2P sub K minus P sub K minus 1, right? And now this should be in a form that you're used to seeing from last term, one of those recurrence relations, right? Now, if we want to solve the characteristic equation, what's that going to look like? Okay, you solve the quadratic to get the roots. Good. What's the corresponding quadratic equation going to look like? Be chi squared, right? I can just do it right here. Chi squared, yeah, minus 2 chi, because so I'll put the 2 over here, so that'd be a minus 2 chi plus 1 equals 0, right? So chi equals what? -1. Good. Okay. So if chi is -1, then I have the general form of my solution, which is going to look like this. I'm going to have P sub K equals, remember it's A times -1 to the K plus what? Oh, should it be 1? Oh, yeah, it factors to -1. So this would be a +1. Yep, thank you. So this is +1. Thank you. So this would just be 1 to the K plus what? Good. I'll throw a different coefficient on there. Yeah, exactly. B, K, 1 to the K. Okay, well, the 1 to the K factors go away. So really what I've got here is P to the K, or sorry, P sub K equals A plus BK. That's my general solution, right? Now what do I do? Plug in initial conditions. Excellent. And what are my initial conditions going to be? Let's set these over here, the initial conditions. One equals n. I'm not quite sure what you're getting at there, David. I didn't say this quite right. Probability of having K dollars and winning. Sorry, I forgot a little thought there. It's important to have the right thoughts or else it doesn't work. So, what's the probability of having $0? Oh, am I doing this wrong? And losing. Sorry, wrong one. Gotta say it correctly. Losing. All right, there we go. Yeah, there we go. So P sub K is the probability of having K dollars and losing and being ruined, right? And losing all your money, right? That's why it's called gambler's ruin, because we're trying to find the probability of being ruined, right? So what's the probability of having $0 and being ruined? Yeah, the opposite of what you wrote. The probability of having $0 and being ruined is 100%. If you get $0, that by definition means that you're ruined. But if you have M dollars, that means that you stop playing. So there's 0% chance of you being ruined because you won the game. You made as much money as you wanted to, and now you're going to stop, right? Okay. So I have these initial conditions now. I do have now the correct definition of P sub K. And now we can solve for A and B using the initial values from our recurrence relation, right? So if I have P sub 0 equals A plus B times 0 equals 1, then what does that tell me? A equals 1. Okay. P sub M equals A plus B times what? Not 1. M, good, equals how much? 0, which tells me what? B equals negative 1 over m, right? So I've now got my values for my coefficients. I can say, okay, well, my probability of being ruined with k dollars is how much? Well, it's 1 plus negative 1 over m times k. So in other words, negative k over m. And there's my final answer. Maybe I should say 1 minus k over m. How about that? Make it a little shorter. Okay. In that case, let's go back to my original question. Let's say I want to double my money, right? I start out with $100 for n, and I'm going to play up till $200, right? So what's the probability of being ruined with n dollars if I'm playing up till $200, which would be 2 times n, right? It would be 1 minus n over 2n, right? So 1 minus a half is 50%. So in this particular game, if you try to double your money, right, then you have a 50-50 shot of doubling your money, right? Which if you think about it for a minute, right, you have a 50% chance of doubling your money and a 50% chance of going broke. And if you find the expected value from that, right, you have a 50% chance of getting double your money minus, plus a 50% chance of getting $0 going broke, which of course gives you back the n dollars you started with because it's a fair game, right? So the expected value of playing is that you'll maintain the however much you started with because, because it's fair. So you're just as likely to win as you are to lose. So however much you start with, that's how likely it is that that's the expected value of the amount that you're going to maintain. But what can go wrong? You get greedy. Okay, well, why would that be bad, David? Yeah, once you go over double the winnings, the probability of losing increases. Let's say that you want to triple your money, right? So instead of doubling your money, you stop when you get $200. Let's say you stop when you get $300. Well, the probability of losing, if you're trying to triple your money, is going to be 1 minus n over 3n, which of course is going to be 1 minus a third is 2/3, or 66.6%. So if you try to triple your money, your chances of losing increase significantly, right? Now you have a 2/3 chance of losing instead of a 1/2 chance of losing, right? So the more money you try to make, the less likely you are to get there, which makes sense, right? Hopefully that makes sense. Really, the issue here is that if you start out, think about a number line, right? We have like a number line here. We have, 0, 1, 2, all the way up to 100, and here's 200. And you start off here, right? Now, you're just as likely to win as you are to lose, right? So you're just as likely to win money, which would be going this way, as you are to lose money, which is going this way, right? So as you play, your amount of money sort of bounces all around on this number line, right? Um, and you know, you sort of win a bit, and then you lose a bit, and then win a bit, lose a bit more, win a lot, lose a little bit. You know, you're sort of bouncing around. But what's problematic about this? Why aren't, let me put it this way, why aren't you guaranteed to just keep your same amount of money you started with? I mean, if it's a fair game, right, and you're just as likely to win and lose, why isn't your expected value just however much you started with? Or is it? Yeah, if you grow broke, you have to stop playing, right? As you play more and more games, it becomes more and more likely that you hit zero, at which case you have to stop because you don't have any money to keep playing with, right? So that's really the whole problem of Gambler's Ruin, is that you're not starting out with an infinite amount of money like the casino is, right? For all intents, so for all intents and purposes, the casino has infinite money in the sense that um, they have more money than you, right? And so because they have more money than you, they can play more games than you, which means they have a high probability of being able to force you down into being broke before they go broke, right? So really Gambler's Ruin is the idea that if you play enough games, eventually you're either going to hit zero or you're going to hit your winning amount. But if you don't have a winning amount, if you don't have any point that you're stopping at and you just keep playing, you're guaranteed to go broke, right? If you keep playing long enough, right? Because eventually you'll bounce around, bounce, 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 and eventually you'll hit zero, which means you're broke and you're ruined and you have to stop playing, right? That's if you don't have a stopping point, which is why it's always good when you gamble to have a stopping point. Because if you don't and you just keep playing, eventually you're guaranteed to go broke. And that's what Gambler's Ruin is. What do you guys think? Does that make sense? If you have a lot of goods to pawn, you're okay. Well, if you have a lot of really expensive stuff to to gamble with, then really the question is when you're playing a game like this, the question is who has more money, you or the house, right? And whoever has more money is more likely to win the game, just like poker, right? You know, if you're coming into a poker game being able to gamble with more money, you're starting with more. Um, then you know then you're more likely to win the game, right? Whoever is the chip leader is most likely to win because they can play longer, they can afford to spend more before they are ruined and hit zero, right? Yeah, so this is pretty fun. I think it's a pretty interesting way of thinking about gambling and playing games. So yeah, it's pretty interesting. Does anyone have any questions for me on that? Okay, so let's take another short break. Let's take 5, and we'll come back and talk about random walks. So we'll be back in 5. All right, so for the last half hour here, I wanted to talk about a random walk, okay? And really what I'm asking here is if I'm just as likely to go one direction as the other, how many steps does it take to get all the way down to zero? Or maybe phrased a little bit differently, after n number of steps, on average, how far am I away from my starting place if I'm just as likely to step one way as another? So there's a technical term in math for this. It's called the drunkard's walk, or random walk. So after you go to the casino and you get all those free drinks and you lose all your money and you're ruined, right? After you leave the casino and you start to walk home, you take the drunkard's walk, right? And what that means is that you start at some point, for simplicity here, let's say that we start at 0, right? And you're just as likely to walk to the left as you are to the right. Okay, so you start at 0. Here's my start. And I'm just as likely, 50%, to go this way as I am to go this way. Okay? So let me ask you a question. What's the expected value of your position at any point during the drunkard's walk? If you're just as likely to go one way as the other. 0, right? So at any time, you're just as likely to go right as you are to the left, so your expected value of your position is always 0. Here's a different question. So EV of position is always just going to be equal to 0. But a different question, what's the expected value of your distance from the starting point? Now, that's a different question, right? Because now your position isn't negative on one side and positive on the other. Right now you're at distance, which is positive either way, right? So it's not like the negatives are going to cancel the positives now, right? If you go to the right, that's a positive. If you go to the left, that's a positive. So I'm wondering, what's the expected value of your distance after, a given number of steps, right? So for this, I'm going to have some function of the number of steps is going to give me my expected value of my distance from my starting point. It is going to be another Pascal's triangle thing. That's exactly right, Lucas. So let's do some examples, okay? So if we were to take, let's make a little table, right? So so over here, I'll say, let's have my number of steps be n, and then my EV of my distance over here, okay? Now, IST, okay. So if I take 0 steps, what's my expected value of my distance from the origin? After 0 steps. 0, good, right? Because I haven't gone anywhere yet. How about after 1 step? Okay, then my expected value is going to be 1 because I have a 50% chance of going this way, which means I'm 1 step away, or I have a 50% chance of going that way, which also means I'm 1 step away. So either way, it's a 50-50 shot, but either way, I'm going to be distance 1 from the origin. How about after 2 steps? What's going to happen? Now there's a few different possibilities that could happen, each with their own separate expected value. So how's that going to look? Good. Either at 0 or 2 or -2, right? So how many different sequences of steps can I make? Let's call my steps left and right. So I can either go, my steps could be either L or R. Okay, good. So for distance 2, or for 2 steps, right? So let's say 2 steps, I could go left, 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 right, right, left, or right, right. Okay. And each of these is a 1 in 4 chance because it's all random, right? So these are all equally likely to happen, right? So in that case, what could go down? Well, if I go left, left, then I'm at -2, which means I'm distance 2 from the origin. And what's the probability of that happening? So this is a 1 in 4 chance that I get left of being distance 2 from the origin. So what will my expected value be for that? Yep, so you got the right idea, Sean. So this guy would be would give me an expected value of distance how much? Yeah, so this would be 1/2. These guys together is 2 out of 4 times what distance from the origin? So if I go left and then right, or if I go right and then left, that's times 0. So this guy gives me an EV of 0. And right, well, that's a 1 out of 4 chance. Again, times a distance of 2 from the origin, which gives me a distance expected value of, again, 1/2. And of course, for the total EV, I add these up. Which is 1. So after 2 steps, my expected value of my distance from the origin is still 1. But it's a little bit different because with 1 step, I could be either here or here, right? With 2 steps, I could be here with 1/4, here with a half, or here with a quarter. But again, that, sort of when you average it out, comes out to expected value of 1 unit away from the origin. What do you guys think? Does that make sense? Questions so far? Okay, so what if I was to go 3 steps? Well, I won't make you list out all the combinations, but let's list out the probabilities and their distances, right? So there's sort of like 4 things that could happen, right? Well, let's start out with going the furthest to the left. So in 3 steps, what's the furthest I could go left? -3. And what's the probability of that happening? Left. 1 out of 8. So I have 1 out of 8 times 3 is 1 possibility. Okay. What else could happen? Well, it's like Pascal's triangle, but it's not exactly Pascal's triangle. We're gonna see it in a minute here. So what else could happen if I was to go 3 steps away? What other number could I end up at over here on the left side of 0? Yeah, -1. Okay. And how many different ways could I get to -1? 3 ways. I could go left, right, left, or right, left. So 3 out of 8 ways of doing it times a distance of 1 from the origin, right? What else could happen? So the expected value is the largest number in the row of Pascal's triangle. Not quite. Not quite. Okay, so what else could happen besides ending up at -1? Where else could I end up? +1. Okay, so for +1, I could go right, left, right, or left, right. So 2 rights and a left puts me at +1. So what's my computation going to be for my expected value in that case? Good, 3/8 times 1 again. Same thing, just on the other side. sort of the mirror image of the left-facing one. And speaking of mirror images, what's my last value going to be here? 1/8 times 3. Because I could go right, 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 which gets me all the way over to 3, and there's a 1 out of 8 chance that that happens. What's my grand total? Good, 3/2, right? 12/8 is 3/2. Beautiful. So not really a maximum in the triangle exactly, right? Let's try one more, just one more. Let's try it for 4. Now Pascal's triangle is involved here, right? How does Pascal's triangle factor in? Like, where is Pascal's triangle in this little equation here?
So you could end up 4 steps away
Mm-hmm.
with a weight of 1 divided by 2 to the 4th. The 4 being the biggest number you can get to with 4 steps,
Mm-hmm.
and also the biggest number, the biggest coefficient that shows up in Pascal's triangle on the 4th row.
Yep.
And the 1 over 2 to the 4th being that shows up, that it has a coefficient of 1, and the total number in that row of the triangle is 2 to the 4th.
Beautiful.
And you can do that for each of them, are going to kind of correspond to each other like that.
Okay, so what's the next term going to look like?
It's 1441 or
146.
14641. So the
That's
next one is going to be 4 over 2 to the 4th times, you can end up 6 steps away. No, that can't be right.
So
Something like that.
let's do let's do an example. So here we're going mostly left, but 1 to the right. So we could go left, 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 right. Right? 4 lefts and a right. Yeah, so it'd be a 2, right? Or what's my next term going to look like? Okay, 6 over 2 to the 4th times, not times 1, should be 0. Yep. Plus. So here's where Pascal's triangle comes in. The Pascal's triangle coefficients come in as the numerators here, right? The denominator is always going to be 2 to the 4th, right? Which is, again, the row sum for Pascal's triangle at that point. The rest of the terms are going to mirror the first ones. So I'm going to have plus 4 over 2 to the 4th times 2 plus 1 over 2 to the 4th times 4. And here's the remaining entries from Pascal's triangle showing up here in the numerators, right? These guys, 42024, well, that's kind of interesting. Those look a little different, right? We'll have to be a little bit careful about those. Where these numbers are coming from, 42024. Here we had 3113. Maybe those are related to Pascal's triangle, maybe not. We're going to have to be careful about that. Here we had 202. So the amount that we're moving from the origin doesn't look like is really related to Pascal's triangle. It's some other weird numbers. But the numerators of our probability fractions here are certainly the coefficients from Pascal's triangle. Well, let's add this up. What do we got here? So we got a quarter plus, how much is this? This is a half, a quarter plus a half. This guy's 0. And then we have the same thing on the other side, right? So 3/4 times 2 gives me 3/2, right? And now that's interesting. It's a nice little pattern going on. Well, we start out with 0, then we have 2 1s, then we have two, 1.5s. And so can you establish a theory about the pattern that's happening here? Could be multiple theories. Next one will be 1.75. Okay, why do you say that, David? Increments going down by half. Okay, maybe. Should we compute it? But why don't we do this? Why don't we find a formula for what's happening here, and then we should be able to just plug in n and get out the expected value at that distance. So can we come up with a formula for this kind of thing? How could we do that? Well, okay, so let's start with the easiest part. So the main thing the main operation that's happening in this formula is what? What's the outermost operator going to be in terms of parentheses? Addition, right? So the formula is going to look like a big summation, right? So if I want the EV in terms of the number of steps as a function of n steps, right? Well, it's going to be some kind of summation, right? Okay, where does the summation start and where does it stop? So what's our starting point? What's our stopping point? Okay, sum from k equals 0 to k equals n. And we want n choose k times the distance from 0. Okay, so you're thinking from k equals 0 to n of n choose k times what now? Times distance from 0. Okay, so I'll just abbreviate that. I don't know what that is yet, so I'll just say dist. And then I think times one more thing. There's one part that we missed. Good, 1 over 2 to the n. Can't forget this part. Okay, so here's this part of the formula in pink. Here's this part in yellow, and then the distance, well, that's going to be these guys, right? Is everyone happy with that? Does that look okay to people? We still haven't figured out how to find this yet, but does my sort of organization of those terms make sense to people? See where it came from? Makes sense. Okay. So then let's think about this distance situation, right? How can I sort of get it to pop out 42024? Or can I get it to pop? So I want, for zero, I would want a 4. This would be term number 1, term number 2, term number 3, and term number 4. So is there a function I can use to get, 42024 out of those numbers? The absolute value of n minus 2k. Okay, so good. So I could do it that way. I'm a little bit worried though about solving this guy, because of course I do want to find a closed form for this, right? So I'm a little bit concerned about that absolute value and how that's going to play in my solution of the closed form for the sum, because we haven't done any like that before, right? I'm a little bit worried about that. Is there another way that we could think about distance that could make this a little bit easier and even reduce the number of terms that we need to look at? Does anyone see a little simplifying trick? Yeah, all that we need to do is go to the halfway point and multiply each of these guys by 2, right? Because these two are equal to each other, these two are equal to each other, and this one is multiplied by 0, so it doesn't contribute anything. So all I really need to do is ignore these first 3, compute these 2 guys, and then double the result to account for the 2 that I skipped over here. Then the middle one doesn't contribute anything, right? So another way of looking at it is I could say, okay, well, this is going to be the sum from what? Well, actually, I could even just take these first 2, right? Double these 2, and then forget about the last 3. Maybe I'll think about it that way. So I go from k equals 0 up till how much? Well, for 4 steps, I want 0 and 1, right? So I would go k equals 0, k equals 1. So I'm going up till n over 2 minus 1, right? Because n is equal to 4, and I just want 1 and 2. It won't work for odd n. You're right. But let's circle back. So that's great, Sean. It's going to be different for those. But let's circle back to that in just a minute, right? Now I'm going to take double this whole thing, right? And now what is my distance going to look like? Well, I'm still going to have n choose k. That's still going to be in there, right? And then what is that going to be multiplied by? Well, there it's going to be 4 in the first one, 2 in the second one. So it would be multiplied by how much do you think? N minus 2k. Very nice. Now that's a formula that we can work with, at least somewhat, without the absolute value, right? So now we've eliminated that absolute value from our formula, which is kind of nice. Now we don't have to worry about finding that closed form, right? But now we have this big old mess, right? Oh, and by the way, this is all multiplied by 1 over 2 to the n, which I should probably pop out to the front here because I'm multiplying that by a constant amount inside of each term. So I could just pop that guy out to the front, right? 1 over 2 to the n. I've kind of run out of room here. So let me rewrite. So what I've ended up with here is my expected value of my distance, n steps away, is going to be 2 over 2 to the n times the summation from k equals 0 to n over 2 minus 1 of n choose k times n minus 2k. Okay. I'm not sure if we can solve this yet, right? But we'll think about it for a moment, okay? Before we try to solve this, let's see if we can do the other kind, the odd formula, right? Maybe that one will be easier, right? So if I was thinking about the odds formula, well, maybe I should try the next one after this, if I do 5 steps. So for 5 steps, I'm going to have 1 over 2 to the 5th times something, right? Plus 1, 5, 10, 10, 5, 1. Right? So how many steps am I going to be away from the origin in this first term? 5, right? How about in the next term? 3, and then 1. And if I do this, and the exact same thing on the other side, I can do that same trick where I multiplied by 2, right? Everybody see that? Because the last 3 terms are going to be the same as these first 3 terms, right? Because the triangle is symmetric, and so is the number of steps. I go 1, 5, 10, 10, 5, 1, and similarly I go 5, 3, 1, 1, 3, 5 on the other side. And since it's symmetric, I can just take my total and double it, right? So here's another formula for an odd number of steps, right? Let's see if you guys can get this one. So what's my starting coefficient going to look like? Okay, so the starting coefficient here is going to be double whatever my total is, divided by 2 to the n as before. Same thing as last time. Because I'm dividing by 2 to the n right here, right? But in every term, so I can factor it out of the sum. And I'm going to double my grand total, right? So I have 2 over 2 to the n. Oh, and Lucas, you got an idea there. Okay, times the sum from k equals 0 up to, is it still n over 2 minus 1? So that would be n minus 1 over 2. I see. N minus 1 over 2, right? Times n choose k times, again, n minus 2k. So that's n minus 2 times 0, n minus 2 times 1, n minus 2 times 2. Yep. So my formula is the same, my coefficient's the same. The only thing that's different is the amount that I count up to, depending on if I'm on an even row or an odd row, right? So for even n, the formula would just be from 0 to n over 2 instead of n over 2 minus 1. Well, we could include this central term with the 0 in it, and it won't change anything, right? So maybe the right way to think about it is to use either the floor or the ceiling, right? Maybe really what I'm shooting for, if I want to add up 3 terms on the 4-step line and 3 terms on the 5-step line, then maybe I can have a common goal here up top to work up to. If I have a 4 in here, 4 over 2 minus 1, that works. But if I have 4 minus 1 over 2, that'd be 3/2, which is not a whole number. So I wouldn't really want to do that. But maybe I could say, you know, for the number of terms in here, if I want to get 2 of them on this side, maybe I could say, the ceiling of n minus 1 over 2, right? Which if I plug a 4 in there, it'd be the ceiling of 4 minus 1 over 2 would be, oops, there's not supposed to be a bottom on that, which gives me the ceiling of 3/2. Keep doing that, which equals 2. So I think I could have a common formula for these two guys. Oh, and I'm out of time. Sorry, I went over a little bit. But I could have a common formula for these if I just did either a ceiling or a floor type of computation. But these are so close together that it looks like you're going to have the exact same formula for an even row as you're going to get for the odd row afterward, which we can see right here in the table, right? Or I'm sorry, for an odd row and then the even row afterward. So if I have 1 step, it's going to be the same as 2 steps. If I have 3 steps, it's going to be the same as 4 steps. And that's because if you look at these two formulae, then we could massage this top term to make them actually equivalent if we just use a ceiling, which will make these exactly the same, which is why the odd and then the even have the same number of expected value in our table, right? So I'm out of time, so I should stop there. Next time, I'd like to start with this formula and show you how to find the closed form solution. And that's where we'll jump back in next time, and we'll be able to find that expected value for the number of steps in a random walk. Any questions before we go? Okay, great. Well, have a good day, everybody. Good luck on your midterm. Please don't forget, it is due tomorrow at midnight, tomorrow night, 11:59 p.m. And good luck. See you Wednesday.